So this video I'm going to show you how to process a metal organic framework, MOF for short, CIF file into a crystal grower structure file using Topos, and how to set up your first simulation with this structure. So first we need our CIF file. I find this website is quite helpful, so you get access to this CrystalWorks database here, which I've got open in another window. And that gives you access to a lot of databases of CIF files. So the Cambridge Structure database is here as well, ICSD, and a few other ones too. So all I've done is do a database search, and I've searched for MOF5 as my compound name, and it's given me 124 possible CIF files, and I've just chosen this one at random. So this is MOF5 with some nitrogen absorbed in it, and then I clicked export CIF file for this entry, and then downloaded the CIF file. So swapping over to ToposPro Lite, I've created a database and I've imported a CIF file. I've imported the one that I just downloaded, and I've just renamed it MOF5. So it's the same compound, I've just changed the name of the crystal structure. For more information on using databases, watch the second part of the ToposPro for Crystal Grower series. So if we look at the Atoms tab, you can see we've got our nitrogen, our zinc, oxygen and carbon, which makes up our compound. Now if we just visualize our structure with IsoCryst, so click this pencil symbol here, and I'll grow our crystal structure. You can see we've got our MOF, but none of the atoms are connected together. You can make out our metal clusters and our linkers. So let's bond everything together quickly. Can do that using AutoCN, and it works really well just by using the default options. So I'll just click default using domains with a minimum omega of 1.5, and I'll just run that, and it's got some idea of the bonding. So we've got a tetrahedral zinc, which we know is typical for MOF5. So if we visualize our structure again and grow it, can see we've got our connected net, and we've got our nitrogens in the pores, we've got our linkers, and we've got our metal cluster here, all connected together. We've also got the van der Waals, and if there was any hydrogen bonding, they'd have been picked up as well by the AutoCN function. But having all these nitrogens in the pores makes it a little bit complicated, so I'm just going to simplify those down into a single dummy atom at the center of the pore. If I wanted to look at it in more detail, then I would keep the nitrogens in and try and model that structure. But just for this example, I'm going to keep it quite simple. I'm just going to reduce everything down to a single dummy atom, and that can be the species that are in the pore. So first of all, I need to get rid of the nitrogen. So I'm going to go back to my database. And before I change anything, I'm going to create a duplicate of this database entry, because I'm going to change the CIF file, and I want to make sure I've got a backup of the original. I'm going to change the name of this to MOF5 no N, because we're moving the nitrogen, and I'm just going to delete this nitrogen atom and press save. Well, because we've deleted an entire species, it makes sense to recalculate the AutoCN, so I am going to do that. So I'm going to say no here, and if I visualize the structure, it now has no bonding again, but we've lost the nitrogens, so I'm just going to run AutoCN with the default options again. And now we've got our empty pore MOF5 here. We found through previous research that you need to also account for the species that fill the pore in the MOF when you're growing the crystal structure. So that's one of your key units of growth, are these species that fill your pore. So we had absorbed nitrogen to begin with, but we're just going to simplify that down into a single dummy representative atom at the center of each pore. So we know we need to add a species right at the center of the system here. That'll be our 0.5, 0.5, 0.5 coordinate. So we can go back to our database entry and add that in. So if we just double click, we can add another species here. So I'll call this one barium, because barium isn't in my crystal structure. And I will put it at a position 0.5, 0.5, 0.5. If I press save, I'm not changing any of the bonding this time, so I'm going to keep all the data I've calculated already. And if I now visualize this structure, we've got our central atoms here, but we don't have them in every single pore yet. So if you look closely at the MOF5 structure, the aromatic rings point in different directions in each pore. So in this pore, they're pointing inwards, so they're face on, whereas on the outer pores, they're pointing edge on. So the environments are actually slightly different. So we can add a second atom, and I'll use a different atom type as well. Then we can actually change them independently and give them different energies. It might be overcomplicating it by adding a full species into the system, but if we find it's not necessary, then we can treat them with the same energy, which would be as if we were treating both as a single solvent or pore species. So if we added one at this position here, the 0.5, 0.51 in the Z, or 0, then it should add one at all the symmetry equivalent positions. So I'll go back to my database entry. I'll add another species here. This one I'll just call gold, and I will set that as 0.5, 0.5, and 0. So if I save that, I'll keep all the data again, visualize the structure, and we've got our dummy atoms at the centers of each pore. So now we want to add some bonds between our dummy or metal atoms that represent the pore species and the rest of the framework, so bonds to maybe the linker. So I'm going to recalculate our bonding with these extra species added in using AutoCN. So I'm just going to run AutoCN with the default options and see which things it picks up. So I'll set default, and I'll run. And it's picked up connections to the gold dummy atom, but none to the barium. So I just want to add some barium connections on top of the net. So the easiest thing to do is to use the ranges algorithm in AutoCN. So this is where you specify distance ranges to pick up interactions between. But we have to exclude all the ones that we don't want to see. So first of all, we need to think of all the species in our system. So we've got carbon. We don't want to see any interactions coming from carbon, so we'll have to list all the species that we don't want carbon to bond to. So we don't want to see C to C bonds added on top, because we've already got those. We don't want our C to O bonds added on top. And we don't want our carbon zinc bonds to be added, because those don't exist. And then we need to think of our oxygen. We don't want our oxygen to zinc to be added, because we've already got those. And we don't want our zinc to zinc connections either, because those don't exist in our framework. So I'll click this keep matrix option. That'll keep our last matrix saved, and we're just going to add to it. So I'll just run this now, and you can see it's added nothing. So we're just going to focus on our barium connection. So we want our barium to carbon, because that's the linker, because we want to connect it up to the linker. And we'll say from 0 to 8 angstroms and see if that picks anything up. So that's none. Let's bump this up slightly to 8.5. Run that again. Still nothing. Let's try 9. Still nothing. Try 9.1. Still not enough. 9.2. And then we've got our barium connections there. So it's picked up 72 interactions that are going from barium to carbon. So if we now look at our structure, we've got a lot of these interactions originating from our barium, and they're just going to the 6 carbons around the aromatic ring. Whereas the gold is only interacting with 2 carbons on each aromatic ring. That's because of their orientations being different. So all we did there was capture as much of the bonding as quickly as possible with the default options for AutoCN, and then adding the missing ones on top that we wanted. So if we wanted to look at the pore species interacting with the metal cluster, we could have used an atom that was present in the metal cluster instead of the carbons on the linkers. So now everything's bonded together, we need to have a way of separating it into our units of growth. So we're going to have 4 units of growth here. We're going to have our linkers, our metal clusters, and then we're going to have our 2 pore species. And the easiest way to do that is to separate them by assigning them different bond types between each other. So, for example, hydrogen bonds. Because everything's currently bonded as valence bonds, if we had hydrogen bonds, then we could say that hydrogen bonds denote a separation in molecules, just like we would for a full molecular crystal. So I can do that in the database entry by going to the adjacency matrix tab. And if I change all the interactions from gold into hydrogen bonds, a shortcut here, you can highlight everything that's equivalent by space group and right click to change type. And then we could do the same for this set here. And then the last thing we need to do is to separate our linkers from our metal clusters. So I'm going to change the zinc to oxygen bond. So if I open the zinc here, I've got 3 oxygens here that will correspond to the oxygens on the linkers. There is another oxygen, but that's at the center of the zinc tetrahedron. I can change those to H bonds as well. If I visualize that structure, we now have everything separated by hydrogen bonds, but within their own species they're linked by valence bonds. So if I turn off hydrogen bonds, you can see we've got our 4 units of growth. We've got our linkers, our metal clusters, and our 2 different pore or solvent species. So now that these are separated, we can run ADS to calculate our structure file by calculating our simplified net. So we're going to do a simplified net. We're going to keep the initial structure so we can draw the molecules in the Crystal Grower Visualizer later. We'll go to the Topology tab. Valence bonds are atomic and hydrogen bonds are between molecules. That will separate our species into molecules, and then we can run ADS and choose whole molecules as we would for a molecular crystal as our central species. And then it will calculate our simplified net. So if we open this in IsoCryst, we'll be able to see the dummy atoms that have been added in. So we've got a dummy atom at the center of our metal cluster, another dummy atom at the center of our linker, and then there's one at each of these pore atoms here just hidden inside those spheres. So ZA is our linker, ZB is our metal cluster, ZC and ZD are our pore atoms. And they'll appear in this order in the structure file. So linkers will come first, then metal clusters, then our pore atoms. So if we look at our structure file, we've got our 10 species, our 1, 2, 3, 4, 5, 6 linkers, 2 metal clusters, barium, which denotes one type of pore atom, and then gold, which denotes our other pore atom. As this is a net structure, we also need to export the corresponding net interaction file with the structure file, also called net.txt. So we need to do this by clicking Database, Export, and then picking a location to save. I'll just save to my desktop, and I'll call this mof5_pore. So now we need to set up our crystal grower simulation. So I've opened the user interface. I'm going to select a net-based structure, and I'm going to load my structure file. So from my desktop, I've got this mof5_pore. I'll press read structure file. And you can see it's loaded it successfully. So now we need to do the same for our net.txt. Read that. And here we get to decide all our interactions. So we've got our linkers first. And you can see there's one short length interaction, which has been marked A. And there's 2 longer distance interactions, which have been marked B and C. So A will be our linker to metal interaction, and B and C will be our linker to solvent interactions. And then we've got our metal clusters down here. They only have one interaction. That's our metal to linker interaction. And then we've got our solvent to linker interactions, E and F. So we'll be able to control those when we get to our net options tab. So I'll confirm interactions. And then I'll just set up the rest of my simulation. So I'll just run a simple simulation with no screw dislocations, save a checkpoint. I'll create a new folder and I'll name the simulation results MOF5 pour. And I'll save it to my simulations folder, just in my documents. And I'll select this folder to save my results in. I'll leave everything else as is. I'll just set the temperature a bit higher. I'll set it at 120 degrees. And I'm running for 10 million iterations, so that should give us a nice sized crystal. And I'll make a movie of 20 frames. Starting from the beginning, equally spaced throughout the simulation. I'll run in supersaturation mode 3 to find the equilibrium point. And I'll set my driving force to start with as quite high, as 100, just to make sure it nucleates. Half the simulation, so 5 million iterations at high supersaturation, and then 100,000 iterations to reach equilibrium. So now if we go to our net options tab, I'm just going to leave the bond weightings as the same. You can see it's read in some strange numbers from the Topos file. That's because we calculated the framework to start with using domains, so it could calculate these values here, these solid angles. And then we calculated the second pore species using ranges. So no Voronoi Dirichlet polyhedra were calculated there, so no solid angles were calculated. It was just a straight distance between the species. So that's why this value is 0. So we need to change these to some more sensible numbers. So interaction type A we knew was our metal to linker interaction. So that should be quite high. So I'm going to set that as 8 kcal per mole. And then our B and C interactions were our interactions from linker to solvent. So these are a bit strange because when you think about crystallization, you're thinking about taking your species from solution or from solvent and putting them into the crystal phase. So the energies that we're putting in here are replacement energies for replacing a neighbor. So this example here was linker to metal. If we replaced a metal species with a solvent or solution species. But if we're talking about the solvent, we're replacing a solvent with a solvent. So the energy for this interaction would actually be 0 because we're not replacing any of the neighbors. The neighbor is still the same species. And this is an important thing to think of whenever you consider solvent in your crystallization as a unit of growth. So this energy would be 0 as well. And then we've got our metal to linker interaction, so that's the opposite direction. The energy is not essentially the same, free energy of crystallization, but in this case I'll put it as the same. Now these values here are our solvent to linker interactions. So in the solution, the solvent is surrounded by solvent, but it's now surrounded by linker. So there has actually been a replacement there, so these do have an energy associated with them. So I'm going to set this as quite low. I'm just going to set this as 2 kcal per mole. And I'll set it as the same for each species. And then crystal coloring, I'll just tell it to find the facets and we can run our simulation. And now our simulation's completed. We can go to the folder where the XYZ file's stored and open it in a Veto, which I've done in the background. And then we've got our 20 frame movie of MOF5 growing. So you can see we've got a nice cubic crystal. The layers have been identified quite well. And the surface is quite rough and rounded because it's been growing around equilibrium for the last half of the simulation. So that was a walkthrough on how you set up a MOF calculation. MOF5 is one of the simpler MOFs, but the concept applies to all other MOFs. As long as you separate your metal clusters and your linkers distinctly, and then add in your pore filling species, then you should be able to tackle any MOF that you come across with Crystal Grower.